Hi, welcome to the Signal Path. In this episode, we're going to take a look at this Stanford Research Model DS360, which is an ultra-low distortion function generator. Now, why would you ever want something like this? When I used to be a PhD student, there was another student in the lab who was designing ultra-high resolution ADCs, and these were running at low speed, but nonetheless, they had very high number of bits, 24 bits or so. And he was using this instrument as a source for testing his ADC. And that's because this thing is such a clean source that when you use it, you're going to make sure that you're measuring your device under test and not your source generator. If this thing has a poor THD, then you just basically measure this thing. You would never know what the performance of your data converter is. And ever since, I've really wanted one of these in the lab, so now we have a chance to work on this. Now keep in mind that a normal arbitrary waveform generator may have a THD of, let's say, 50, 60, which already would be very good, but this thing is over 110 dB, so it's extraordinarily clean. It doesn't do much beyond that. It does have some other functions like ramp and pink noise generations and even two-tone generation, which is fantastic. If you ever work on audio equipment, this is kind of the instrument you need. And even though it looks dated, it's actually still something that Stanford Research sells, and all of their instruments kind of have this look and feel to them. So let's go ahead and turn it on and see what happens. All right, let's see. There we go. Now it passes a self-test, and you can change everything like that. This is the frequency. And let's see, we have amplitude here. It's 420 millivolt RMS right now. And nothing happens when I change this. Now this seems all normal, but if I remember correctly, as soon as you change these, you're going to have to hear a lot of relays click in, and we'll talk about why that is, but I don't hear anything. So I'm a little bit skeptical if this is actually working at all. Now we should connect an oscilloscope to this just so we can take a look at the output waveform, but I already can tell something is not right. Okay, here we're connected to the Keysight scope here. I put something underneath so that there's no glare on the screen, and yeah, there's nothing coming out. So no matter what I do here, change this around, nothing happens. Frequency, nope, nothing happens, unfortunately. Doesn't seem like it's doing anything. And for example, changing between unbalanced and balanced input would certainly have some relays clicking. So nothing happens. And if I connect it to the sync out, there, let's see, do I get anything from the sync out? Nope, I don't get anything from the sync out neither. So yeah, something is unfortunately, oh, something did change there for a second. Yeah, something does happen, but yeah, it's not working. So there's definitely a problem in there. So let's take a look at the operation of the DS360. Even though there's no schematic available, there's a lot we can learn from this block diagram and some of the descriptions that are provided in the manual. So first thing is that there is a display, control, CPU, and so on. And that's obviously working in our instrument because we can change all the values that are displayed and everything. So that part is probably okay. Now let's say you want to create a sinusoid. There are many ways to create that, and in the early 90s the concept of direct digital synthesis was still pretty new, and the fact that this instrument relies on it shows you that they were really thinking about how to do this even all the way back then. So the idea is pretty straightforward. Let's say you want to create a sinusoid. Well, if I store all the parameters, all the data points in the digital domain in some memory, I can then feed it into a D2A converter on some very precise clocking, and then the D2A will create a sinusoid for me. And if I want to change the frequency of that sinusoid, I don't necessarily need to resynthesize everything. I will just change the phase accumulator functions and the way that data is fed into the D2A. So the concept of DDS is now really well established, and there are many clever ways to do this. But this combination has several advantages because you can get really nice and low jitter. And importantly, your D2A will need to run at a fixed clock frequency, and just the way you feed the data would have to change. So the data changes, but not the clock. And therefore, you can put an anti-imaging filter, which is a fixed filter, and get rid of all of the aliasing tones and all the other distortions that come from the D2A due to its clocking. Now this anti-imaging filter in this situation is still a 7th order filter, so you really have to build a really good one, but this combination of a DSP, D2A, and anti-imaging filter is a powerful idea for using DDS to generate signals, and that's exactly what they've done here. And then after that, we do have a distortion reduction filter, because even though you're building this a 20-bit D2A and everything else that follows, it's still going to have its own distortion. And this distortion reduction filter is intended to get rid of all the harmonics of the signal. Now you can imagine that this would have to be variable in some way, because if I'm generating 1 kilohertz, the second harmonic is at 2 kilohertz, but if I'm generating 5 kilohertz, the second harmonic is at 10. So we're going to have a unique programmable low-pass filter depending on the frequency that's selected, and that's exactly what they've done here. And using this, you can pretty much remove every remaining distortion that is left. There are limitations here, and that's why this instrument has only a certain frequency range and so on, and this is not so easy to do at very high frequencies, especially as the frequencies get higher and higher and harmonics move further away. But this certainly gives you that really high 110 dB or so of dynamic range. But the job isn't done here yet, because you need amplitude control and everything else. So there is some fine amplitude control circuitry based on some op-amps that they have built there. And after that, they have these power amplifiers for both the balanced and unbalanced output. These are basically independent parallel amplifiers made of discrete components with a very high power supply and a really, really high output THD improvement that you can get over the entire system. Now, if I generate 1 volt peak to peak at a certain THD, it doesn't mean that I can generate 10 volt peak to peak at the same THD if I'm relying on amplification. But I'm relying on attenuation, then I just need to generate a very, very high signal value here and then just put attenuators after it, and then that way you will preserve your THD. And that's why they've done it in this way. So basically you use a DDS, get rid of the clock and all the imaging from the D to A converter, get rid of the THD terms using a low-pass filter, do some fine amplitude control, amplify it by a lot, and create a huge voltage signal. This thing can do 40 volts peak to peak, and then attenuate it with some discrete attenuation, and then put it through some source resistor, which is the programmable source resistor, and then give it to the user. So this architecture works really well for generating these extraordinary good THD signals. And whether it's a balanced and unbalanced signal, then you can reprogram these and figure out where the ground is in the middle. That's all done also using various relays. Now, when you want to create square waves or anything else, you don't need to do it this way. You can just use comparators, because square waves are just square waves. You don't care about their THD, and that's exactly what they've done. The sync function that I was just looking at is coming from some comparator. And then if you're doing some bursts and so on, that goes through a different path as well. You can see the square wave path can also come this way, going through over here. So having said all that, what is the problem with our unit? Well, I hear none of the relays and no activity on the analog board that at least I can hear. And that leads me to think that perhaps there's something wrong from the digital side, because I think these have power. We saw that there was a high power supply voltage coming out of this. So there is power to this board, but no activity. So I think we should work our way backwards and find out what these interfaces actually look like, and see if we can find out if we're getting, let's say, the right signals, or if there is proper digital activity. Now, these main CPU and everything is controlling the front panel as well, so there must certainly be some CPU activity. So I'm a bit puzzled, but I think until we open it and take a look, it will be a little bit difficult. But at least that, I think, is where we should start. And here's the units with the top and everything taken away. It took a while to take it apart because there are actually shields in front of both of these sides. So you can see there is a lot going on here from the top to the bottom. The outputs are on the right side of the unit in this case. So we have our main transformer coming in, this entire digital board. This is labeled 1996, but this one is 2005 because it's many revisions ahead. So they must have been updating this over time. So here, if you start at the bottom, we can see our backup battery here. Here's our main ROM, the main processor over here, and these are all just basically digital stuff. And this ribbon cable goes all the way to the front panel. So clearly this part is working. That's why we're getting this signal out. And I follow this ribbon from the other side, and the only place it goes is all the way up here, reaches here. So it does not touch this board at all. So there's no activity from that, which kind of makes sense because the front panel is working. There's some more logic and so on, some unpopulated stuff here because this thing does support an option with optical outputs and so on, clearly made for, you know, audio applications and so on, but we don't have that. Here's our Motorola DSP, which makes sense also, that showed up inside of our block diagram, and then from there it feeds it to the other side. There's some clever way of doing this. This thing has come off over time, I guess. There's a ribbon cable here and a ribbon cable here that just jumps across. So the only way this board is talking to this board is through these two interfaces. And looking a little bit closer at the top side, we can appreciate what's going on. So this guy over here goes through these three optoisolators. These are really fast optoisolators and low jitter, and they feed our primary DAC. That's the DAC I was talking about. This is an AD1862. So you can look up the data sheet of that one. And after that, what comes out goes through this entire section, and all the functions that I showed you, the anti-aliasing filter, finer output adjustments, and here all the relays that I was talking about. Look how many relays there are here and how much components can be switched in and out. Here's our main output amplifiers, the two discrete components, and they have some heatsink on them with a fan at the bottom which blows over them. So this is the only part that we have high thermal dissipation there. Yeah, looks really nice. So this entire board is powered, otherwise we wouldn't get any voltages coming out. And this is where the power comes from. right over here, and it's coming directly from the transformer. So if the transformer is working and is feeding this side, it must be feeding that side. So we can check that to make sure it is working, but I'm fairly reasonably sure that it is. We have two full bridge rectifiers over here and the capacitors for that power supply. We can certainly check that to make sure those are okay. So now we have a good idea of the architecture of this. We should follow through and see if we can make some critical measurements and see what happens to the digital signal generated in here and how it finds its way onto this side. And let's check the power supply using the Fluke 7089, which I repaired in the previous video. We can measure the power supplies directly on the capacitor voltages. All right, let's turn the unit on. Now the polarity doesn't matter here, just want to make sure some reasonable voltages are there. 34 volts, okay. 31 volts, 19 volts, 21 volts. I think the voltages are fine. So I think I may have found something. So I started digging around at the digital interface side. So if you look here, here's one of the ribbons coming from the digital side. And we have 1, 2, 3, 4 optoisolators, which are connected to this ribbon in one way or another. And this is what isolates these two halves from each other. So I basically started looking at the signals coming into these, making sure that there is digital activity from this side trying to feed to this side. And we can do that measurement together again. So I'm going to go and turn this on. Here we go. And I'm going to try and change the amplitude, which I know should cause some changes on the analog board side. So let's land it on one of these pins. I don't know what these are exactly, what signals they're supposed to be, but we can look at one of them. So here's one. And when I change this, you can see on the oscilloscope that indeed we have some digital activity happening. So some bits are going through. Here's the next one. And this definitely looks like some kind of a clock. Yeah, this is definitely a clock. Look at that. So something's happening. And similarly on the last one, there is something. Yep, this is data. Now if I go to the output side and I do the same thing, you can see I'm getting a really nice signal coming out of that one. And I go to the output side of the next one and I get nothing at all. The output of the third one, I get signal again. So the output of one of these optoisolators has no toggling, and that's actually the clock. But on the input side, it does. See, here's the input of the optoisolator. Here's the output of the optoisolator. Nothing. So that's already pretty interesting. I suggest we remove that optoisolator and try it out. So I removed this. It wasn't easy, and one of the pads came off. So we're going to have to figure out how to repair that, and we're going to measure that optoisolator in just a second. But I did kind of smell something around here when it was running, and I did check, and a few of these resistors are sitting at 150 degrees Celsius. And I worry that might be because without this configuration, there might have been some conflict of registers and turning things on and off that shouldn't be on, and maybe they are burning out because of that. I hope there's no other damage, but anyway, there's nothing we can do. We have to do it one step at a time. So I looked this up, and I know what this is, a part number 6N137, and what do you know it? If I look through my parts, I actually found one that I had ordered from a long time ago for some other application, I think. Look at the date of this, it's 2017. One of the benefits of never ever throwing anything away. So I have a few of these so we can quickly replace it and see what happens. I'll put a socket here because it's really annoying to take off otherwise. So let's go ahead and measure these optoisolators relative to each other. This is the one that I took out of the unit, and this is a brand new one. So let's measure the brand new one. First thing I'm going to do is measure the forward bias voltage of the built-in LED and see how much that comes out as. There you go. You can see I'm connecting it to pin 2 and 3, and it has a 1.2 volt forward bias voltage. Now we can repeat this exact same situation for this one and see if we get similar voltages at all. What do we get? We get nothing. Yep, this is indeed an open circuit. I can flip it the other way too, just to be on the safe side. Yeah, there's nothing. So that makes sense. The LED is broken. Now we can put the good one in the unit. And here it is sitting inside. It looks a little bit unusual with it being the only one that has a socket, but it seems to be sitting correctly. And let's see if that made any difference. If I put it into amplitude control, look at that. Hopefully you can hear it. It is indeed making noises. Yep, perfect. Looks good. Let's connect the output to the oscilloscope and check it out. Indeed, we do get an output now, both on the plus and minus outputs. And if I change it between balanced and unbalanced, the output doesn't change, but the reference ground between the two of them does change. And that does have some implications on the linearity of this thing. But I can change the amplitude. Look at that. I can just keep going. And here it is 12 volt RMS, and it is a very large signal there. Right now we're driving into high impedance, but we can change the output, actually as well the output termination. We can play around with that. Now, there was some heating, as I said, over there. Now that's gone. I can look at it with the thermal camera and things are within reasonable temperature now. But because it heated up so much, now I'm a little bit worried that perhaps there has been some damage to those components, and you cannot tell that by looking at this waveform. If you want to measure 100, 110 dB of THD, you cannot do it on this oscilloscope. Anyway, in fact, that measurement is extremely difficult to do because you need something that has at least 6 dB better THD if you want to measure the signal raw directly coming from the instrument. So we have to deploy some other technique in order to be able to measure that. We're going to talk about that in a second. You must change the frequency to make sure that also works. I actually haven't tried that. There you go, yeah, no problem. It works without any issues. And you can change it pretty quickly. Yeah, it works. So let's talk about what are the challenges of actually measuring and characterizing this now. So to drive in how hard this measurement actually is, at the top here I have the Keysight 33500B series. This is an arbitrary waveform generator, 2-channel. It's still a very good arbitrary waveform generator. It's pretty clean. And I have its output set to 1 kilohertz and 0.9 volt RMS. And it's directly connected to the Keithley 2015, which is a THD multimeter. This is probably our best chance of getting the highest dynamic range on THD measurement here. So right now in this configuration, we are reading about -77, -78 dB of THD, and this is up to the 5th harmonic of 1 kilohertz. And you can see it hovers around a little bit, and the reason it does that is because you need to trigger this properly. As a whole other story. But it is looking reasonable. -77 dB of THD is actually very good for an arbitrary waveform generator. Now I have the Stanford research set to exactly the same settings. I'm just going to move that from here. Same settings, everything. We're going into the positive output here. It doesn't matter which one you go to. Look at that. It basically maxes this out. -99.99 seems to be the lowest value it can display. Anyway, so we're already at the floor of the 2015 DHD. So we really do have to find another way to make sure that this thing meets the spec. At this condition, this should be about -110. So if a direct measurement is not possible, we have to do an indirect measurement. And we're going to take advantage of a similar technique that the instrument does to improve the THD. We're just going to do it the other way around. The instrument uses a filter to get rid of the harmonics. But in this case, we're going to build a 20-notch filter to get rid of the fundamental. Meaning that by choosing these values of these resistors and capacitors appropriately, we can tune this filter such that the fundamental signal will be right in the notch. This fundamental signal is huge, but the harmonics are really tiny. So what we want to do is we want to make sure that this gets attenuated as much as possible so that the instrument that we use can be used to just measure the harmonic alone. And then since we know what signal we are putting in, we can then do a relative measurement, basically do 2 measurements in order to be able to get a THD. It's a very simple idea. It's used all the time in order to be able to make measurements that go beyond the dynamic range of the instrument if the measurement were to be done in one step. The disadvantage is that, of course, you have to build a filter and the measurement takes more time because it is done in multiple steps. But that's the price to pay if you want to find out what the THD floor is. Now, the instrument's manual already gives you very nicely these values because they already anticipate that you will have this problem. And if you want to do performance verification of the unit, this is what they tell you to do. Now, these filters aren't perfect, so even though they attenuate the fundamental by a lot, they also attenuate all the other harmonics that you're interested in, and they give you a correction factor. So, for example, if I measure the power of this to be, let's say, -80 dB, I'm going to have to add 9 dB to that because in reality, that's been already attenuated by this notch filter also. Now, one other thing to keep in mind is that even though these are just resistors and capacitors, it does not mean they're linear. So you have to choose these carefully. In the manual, they recommend thin film resistors and ceramic capacitors, which should have hopefully the highest linearity. Now, with the at 1 volt peak to peak or 1 volt RMS, which is the value we're interested in measuring, that's the highest THD this instrument can give you, this shouldn't be too much of a problem. But don't take for granted that any resistor and capacitor will work fine, because if these guys generate second harmonic also, it doesn't matter that they're filtering the fundamental, they'll leak the second harmonic into this, they will generate that, and you would basically end up measuring the filter instead of measuring the instrument. This is typically what happens when you push so far into the extreme edges of pretty much any kind of measurement, whether it's noise or linearity or voltage or current or time. It doesn't really matter. You always run into these unusual situations. And here's our filter. Now, I'm not using exactly the same resistors I showed you because I didn't have a 7.8 kilo ohm resistor. These are 10 kilo ohm, and that moves the center frequency notch of this to about 775 hertz. So that's where we're going to do most of our measurements, which is okay. Now, this is a perfectly symmetric filter, of course, so the input here and the output on the other side doesn't matter which way you connect it. Now this is still a pretty difficult measurement to make. What you really want is a dynamic signal analyzer or an FFT-based spectrum analyzer with a high impedance input so you can connect the output of this filter to it. Now I actually don't have one of those, and after fiddling around in the lab I noticed that I do need one, so I ordered one. That's going to take a while to get here. We'll use it for some other future experiments. A spectrum analyzer with a 50 ohm input is not going to work. An oscilloscope is potentially possible to use, but that still can have second harmonics show up. So let's use a totally different method and use something else from Stanford research to make this measurement. And here's our setup. We're going to use the Stanford research SR830, which is a DSP lock-in amplifier. Now we're going to use the lock-in amplifier to measure the power of all the harmonics after the filter. I have a few videos about lock-in amplifiers, and one where I've repaired this one. There's a teardown of it too, where I talk about what lock-in amplifiers are, how they work, and a whole bunch of experiments with them. It's going to be a little bit difficult to follow this if you haven't watched those videos, but I'll do my best to explain it. So how does the setup work? We have the output of our synthesizer, the low distortion synthesizer at the top over here. It goes into the filter I just showed you, and the output of the filter comes back and it goes into the A input of the lock-in amplifier. So basically, output, filter, input. So far, so good. But then a lock-in amplifier needs to lock to a certain frequency in order for it to be able to lock and measure the powers you're looking for at different harmonics. So we have a 775 hertz signal which we are using, which is the center of that filter. And if you look at the amplitude of that signal is 1.4 volt RMS. That's the condition we're going to do this measurement. Now because the synthesizer has two outputs, we're going to use the other output over here, and we're going to terminate that directly into the input reference of our lock-in amplifier, and that's how we're going to lock the two of them. So I'm going to turn the output on. There you go, and you can see that this one immediately locks to this frequency. The difference between these two, the tiny difference you see, is because the clocks are not locked in any other way, and there's some difference in there. So right now what are we looking at? We're looking at the first harmonic, so that's the fundamental of a signal of 1.4 volt RMS going to the filter, and when it comes back out, it's sitting at 4.6 millivolt RMS. So it's heavily attenuated by the filter, which is exactly what we want this to do. That's what the whole purpose of this is, to attenuate the fundamental. Now how much is that being attenuated? Well, we can quickly calculate that. We can take our 1.4 volt RMS signal, divide by 4.6 millivolt, and calculate the 20 log of that, and we get about 50 dB, which is what we expect. Perfect. So that looks good so far. Now, in order for us to be meticulous in our measurement, we also need to make sure that the response of the filter is correct for the second, third, and so on harmonics. And based on the filter response, we expect about a 9 dB attenuation on the second harmonic, because the filter, of course, isn't perfect and is going to have some drop at higher frequencies. And we need to measure that to make sure that is also correct, and we need to undo that effect when we're measuring the THD. So in order to measure that, it's pretty easy. Instead of using 775 hertz, we're going to use double that frequency. So we're going to punch in 1550 hertz. As soon as we do that, the filter losses a lot less, of course, so we're going to overload the lock-in amplifier. We're going to increase this range until it comes out of overload there. There you go, there it is. And if you go to frequency, you can see that we now are looking at the frequency of 1.5 kilohertz and the first harmonic. Now we can make this division because the amplitude hasn't changed and see if that number is correct. We can do that again. So we have 1.4 divided by 0.49. And we do 20 times log 10 of that. And look at that, 9.1 dB, almost exactly 9. So everything is correct. Now we can, with confidence, make our measurement. First thing is we're going to make sure we don't forget to change this back to 775 hertz. And this is still sitting in the first harmonic. We're going to go down again in our dynamic range until we are at the right place. There it is. So now we should be able to go to the second, third, fourth harmonic and capture all the powers of those signals. Okay, let's switch that to the second harmonic. There you go. As soon as we go to the second harmonic, we're going to see that this power, of course, almost immediately disappears because the power of the second harmonic is so much smaller. So we need to apply the expansion here and go down in range as long as it's not being overloaded. So we're in some desirable state there. Let's see where it settles to. There you go. So it is measuring about 0.8, 0.87, maybe even 0.9 microvolt RMS is the power of the second harmonic. If I go to the third harmonic, you will now measure the third harmonic power. You can see that the third harmonic power is significantly lower, 0.1 microvolt. Go to the fourth harmonic. There you go. Here's the fourth harmonic. It's a little bit larger, 0.29, 0.28 microvolt. And then the fifth harmonic. We shouldn't really worry too much more beyond that. You can see it's already dropping 0.1, 0.2. Okay, so the significant one, the biggest one, is our second harmonic, and it's going to be the most significant also because it's the one that we need to amplify by 9 dB to counter the effect of the filter too. So what is the total THD based on that? Well, what I'm going to do is I'm going to take this number, amplify by 9 dB, take the third harmonic power, this one, amplify it by 5 dB, and so on with the different numbers of the filter, and if you scale them and add them together, you get 2.6 microvolt RMS, and that's the total amount of power there. So let's calculate to see what our THD is. So the signal coming in is 1.4 volt RMS, so 1.4 divided by the signal I just mentioned, 2.6 exponent minus 6, and that's the ratio. If we do a 20 log of that, what do we get? 114 dB is the THD, and the spec is that you're typically supposed to get better than 110, so this is definitely meeting that. And there's some other calculations you can do, even higher harmonics. There's a little bit of power in there too. If you calculate those, you'll probably end up around minus 110, which is what you would expect, which is amazing. So we basically made this measurement using a lock-in amplifier, which is a little bit unconventional. Now there is a lot more verification steps to really make sure this is working up to the factory spec, but given that it works in the THD, which is one of the toughest, I'm fairly confident that probably the whole thing still works. I'll do a couple of other tests on it just to make sure, but I think we can add this to the lab for future uses. And when I do get that dynamic signal analyzer, we can see if we can measure it raw on that analyzer, because that analyzer itself is supposed to have better than 110 dB of THD. So that'll be exciting. And I hope that you really enjoyed this video. Let me know in the comment section what you think about it. As always, thanks to the Patreon supporters who make a lot of these things possible and enabling getting these instruments and taking a look at them. There's a bunch of reviews I'm working on. Those things definitely take a long time, but hopefully you let me know what you think about it.